Hi folks. Our last section of chapter 2, which deals with inequalities, is learning how to solve absolute value inequalities. And this is actually going to be really similar to what we learned in the last topic with compound inequalities. So with absolute value inequalities, that's going to be any inequality that contains an absolute value expression. And what we're going to find is that when you have an absolute value that's less than a value, then you're going to solve that as though it were an and inequality, a compound inequality. So less than means you're going to solve an and inequality. And if you have a greater than sign, if your absolute value is greater than a value, then you're going to solve that as though it were an or compound inequality. So let's look at these two examples just to start. If x is less than 2, the absolute value of x is less than 2, then that means that x is less than 2 and x is greater than negative 2. Hi folks. The last section in our chapter on solving inequalities is about solving absolute value inequalities. And you're going to see parallels here to a couple things we've learned before. In the last section, we learned about solving compound inequalities, and those skills are going to come into play here. And in the last chapter, we learned about solving absolute value equations, and you'll see similarities to that as well. So an absolute value inequality is any inequality that contains an absolute value expression. So this is a fairly simple absolute value inequality. We have just the absolute value of x is less than 2. With absolute value inequalities, if you see a less than symbol with your absolute value expression on the left, that means that you're going to be solving an and compound inequality. So this ties directly to what we learned in the last section about compound inequalities. But a compound between what two inequalities? Well, this is where this ties back to what we learned last chapter with solving absolute value equations. Because this is the absolute value of x is less than 2, we set up two equations, and this time we do two inequalities, where x is less than 2 and x is greater than negative 2. So if you look at what we're doing, we are not only setting our inequality to a different value, positive 2 versus negative 2, but we're also changing the inequality sign. If x could be less than 2 or x could be greater than negative 2, x is less than 2 and x is greater than negative 2, this is what the solution to the absolute value of x is less than 2 looks like. On the other hand, if we've got the absolute value of x is greater than 2, because this is a greater than sign, we're going to solve this as though it's an or compound inequality. Just like in the previous example, when we have an absolute value, we're going to create two inequality statements. X could be greater than 2, or x could be less than negative 2. Once again, the sign on the value that's not in the absolute value flips, positive versus negative. But when we're dealing with inequalities, we also change the inequality sign. To graph this absolute value inequality, x is greater than 2, x is greater than 2, or x is less than negative 2. We can also have x is less than negative 2 in this direction. So this is a complete graph of the solution. Absolute value of x is greater than 2. So this is the simplest version of an absolute value inequality that you could see. These two examples we've done here. So let's look at more complicated versions where there's actually some solving to do, some algebra involved. The absolute value of x plus 7 is less than or equal to 2. Because this is a less than symbol, we're going to make this an and compound inequality. So I'm going to write down x plus 7 is less than or equal to 2, and I'm going to write down x plus 7 is greater than or equal to negative 2. Look at the two things I did here. I changed the sign on my value that was not in the absolute value, and I flipped the inequality sign from a less than or equal to a greater than or equal to. I was able to do this because I already had an isolated absolute value expression here. And so that's really the first step, and we'll see that when we get down to question D here, where we need to isolate the absolute value expression before we solve the inequality. All right, so now we can work on solving this. I want to get x all by itself on one side of the equation, so I'm going to subtract 7 from both sides, and then I get x is less than or equal to negative 5. And I'm going to do the same thing over here, subtract 7 from both sides of the equation, and I get x is greater than or equal to negative 9. And this is an and, this is a compound inequality. So if I wanted to, I could write all of that in one large three-part inequality. I could write negative 9 is the smallest number I have here, is less than or equal to x, is less than or equal to negative 5. Let's look at another example here. I have 8x minus 11 is less than 0. Now remember, when you have a less than symbol, that's going to create an and compound inequality. But before I get too carried away here, absolute values cannot be negative. They cannot be less than 0. Absolute value expressions cannot be negative. This example here has no solution. Has no solution because absolute values cannot be negative. They must be greater than or equal to 0. So let's look at one that we can solve. How about 8x minus 11 is greater than 13? Here we've got a greater than sign, and so we're going to use the or conjunction to combine to create a compound inequality. So for this example, again, we already have our absolute value expression isolated all by itself on one side of the equation. So I'm going to have 8x minus 11 is greater than 13, or 8x minus 11 is less than negative 13. So those are the two different inequalities we can make from this one absolute value inequality. And then we just solve each one of those inequalities separately until we get x all by itself on one side of the equation. So I'm going to do reverse PEMDAS order, take care of addition subtraction first by adding 11 to both sides of the inequality. I have x, 8x is greater than 24. And then to get x by itself, x is being multiplied by 8, so to get rid of the 8, I need to divide it away, and I have x is greater than 3. For our other inequality that we created, we are also going to add 11 to both sides of the equation, and we get 8x is less than negative 2. And if we divide both sides by 8 here, we get that x is less than 1/4, negative 1/4. So this is an OR inequality. Either one of those can be true. X can be greater than 3, or x can be less than negative 1/4. Of course, just like in the last topic, we can be asked to label these on a number line. So if we did that here, we would see x is greater than 3. Or we could go down to here, x is less than negative 1/4. 1/4. I'm gonna do this here. Negative 1/4 is down here. So this one extends this way. So just like compound inequalities, you can be asked to graph the solution to an absolute value inequality. But I wanted to leave plenty of room for people to do work here. So far, all of our absolute value expressions have been isolated. They've been by themselves on one side of the inequality. However, you can get an inequality that is not isolated. So here is my absolute value portion of this inequality, but I'm also multiplying by 4, I'm adding 1. There's a lot going on this side of the equation. So before I set up the two inequalities, first I need to simplify this. So, not simplify, that's a bad choice of words, but I want to isolate this absolute value expression. So I want to get rid of the 1 and the 4, but I'm going to do this in reverse PEMDAS order, so I'll get rid of the 1 first. Subtract 1 from both sides, and now I'm left with 4 times the absolute value of 2x minus 3 is greater than 16. I can now divide both sides by 4, and I have 2x minus 3 is greater than 4. I now have my absolute value expression isolated. I forgot to write down the absolute value symbols. Isolated on one side of the equation, and now I'm ready to set up the two separate absolute value statements based off of this inequality. I will write 2x minus 3 is greater than 4, and 2x minus 3 is less than negative 4. Look at the two things I did here. I flipped the sign on the value that wasn't in absolute value brackets, and I also changed the direction of the inequality sign. Notice also when I write these two separate statements for my one absolute value inequality, I do not write absolute value symbols in these two expressions. My original inequality had the absolute value symbols, but these two separate statements do not have absolute value signs in them. So to go about solving these, I would, and one other important step I almost skipped here, this is a greater than symbol, and so when it's greater than, this is going to be an OR inequality, or an OR compound inequality. So either of these could be true. All right, to get x all by itself on one side of this inequality, I'm going to add 3 to both sides, and then I get 2x is greater than 7, and then I divide both sides by 2, and I get that x is greater than 7/2. Alternatively, I could have, add 3 to both sides of the equation. I have 2x is less than negative 1, divide both sides by 2, and I get that x is less than negative 1/2. And so we have our kind of solution to our absolute value inequality by solving this compound inequality. x is greater than 7/2 or x is less than -1/2. Let's look at a real-world example of when we might use an absolute value inequality. A climber wants a camera drone. She's willing to pay the mean price with an absolute deviation of $100. Which models meet her conditions? Well, first, let's go and look at what an absolute deviation is. An absolute deviation is the distance between a number and a given value. That given value could be a couple different things. Sometimes it's how far you are from the mean, from the average value. So you're kind of trying to figure out how much spread your data has. Another thing you might be comparing your number to is some sort of textbook value, some sort of true value, seeing how far you are from the measurement you were expecting to get. In this example, she's willing to pay the mean price, the average price, with a certain deviation. So she doesn't want to pay she doesn't want a super cheap model or super expensive model. She kind of wants a mid-range model. So which models meet her conditions? Remember, the average is, to calculate the average, you are going to add up all the values, and then you're going to divide by the number of values that you added up. So in this example, if we want to figure out the average price, we need to add up all of those values, 890, 650, 660, 450, 725, etc., all of those values, and then divide by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the average value here is going to be $6,640 divided by 10. So my average here is going to be $664 across all of those drone prices. So to solve, to set up an inequality to solve this problem, I want my price to be a certain distance away from that 664. I don't care if I'm $100 under or $100 over, so I don't care whether this subtraction problem gives me a positive number or negative number, but I want that difference to be less than or equal to $100. Because my absolute value expression is going to be less than or equal to $100, I'm going to be setting this up as an AND statement. I'm going to have P minus 664 is less than or equal to 100, or P minus 664 is greater than or equal to negative 100. So now, to solve the problem, I just need to solve these two inequalities by adding 664 to both sides of the equation. And I get that P, my price, has to be less than $764. And from this inequality, if I do the same thing, if I add $664 to both sides of the inequality, I get that P is going to be greater than or equal to $564. So I'm going to need to be between those two prices, and I can write this as a singleton three-part inequality. 564 is my lowest number. P is going to be greater than or equal to that, but it's going to be less than or equal to 764. So which of these prices meet this criteria? They have to be between 564 and 764 inclusive. And let's see, this is too expensive, but this one works. This one works. This is too cheap, but this one works. This one works. This one's too cheap, but this one works. This one works, and that one's too expensive. So there are 6 models that meet this climber's conditions of what she's willing to pay for a camera drone. I hope this helped.